I started off going to community college in New York State, and thought I was too smart, and so I didn't go to some of my classes, and that leads to failure pretty quickly. And so I had a stint in the Army to get some money to come back, and did my 3 years, and then went back to community college, got my degree in drafting, and started working in the civil engineering field, doing mostly subdivisions and things like that. Moved to North Carolina about 10 years ago and was doing subdivisions. And as everyone knows, 2008, the housing market crashed, and I felt it first. And so basically you had to kind of change your career. And so I was able to land in a place that was suboptimal, but it was a mechanical engineering firm, and I worked there. But that basically gave me the background I needed to come and work at Morris. I started here as a designer and have worked my way up, and now I am general manager here. It is not typical. I wouldn't say that's a typical route for most people, but from what I've seen of the people that work here, is a typical. There's kind of a type, and we have some people that are engineers and went to NC State and knew they want to be engineers for their whole lives, but we also have a lot of people who come from maybe more of a hands-on in the field type thing, and kind of work their way up also. So I basically tell you this because there's people with many different backgrounds that work here, that come from different, they all have different paths. Some of those people you probably be working with at Wake Tech or in high school. Some of us take a little longer to mature than others, and but we'll get there eventually.
Morris takes great pride in our reputation as a top-tier manufacturer of process cooling equipment, particularly in the poultry industry, where we began some 70 years ago. Our equipment is superior in effectiveness, reliability, and cost of ownership, and M factor is one reason why. So let me explain. Our reputation was earned by more than simple fabrication skills, but rather by something we call M factor. M factor is why clients around the world from a variety of industries call on Morris to solve their most complex process cooling challenges. So what is M factor? Well, it's not obvious by simply looking at our equipment. It starts with rock-solid know-how that can only be gained through hands-on experience, 70 years and counting. We know what works and what doesn't, and more importantly, why. Because of this, we are regularly asked to consult on projects and issues that may or may not result in Morris equipment sales. This know-how is sustained with robust, state-of-the-art design and engineering capabilities at our North Carolina campus. Together with our engineering and design group, the whole company is driven by innovation, focused intently on building a better product and process every day. Every piece of equipment we manufacture goes beyond conventional designs and tackles important issues facing our clients. We pride ourselves in bringing solutions to the market often before others have even imagined them. If you peruse our website, you'll see how innovation drives Morris. In addition to superior know-how and a focus on innovation, another key component to M factor is recognition that our client relationships only just begin with the sale and installation of our equipment. Ongoing support when and where the customer needs it following the initial sale is our promise and practice. Morris knows, particularly in an industrial setting, that efficient and proper operation with no downtime is worth many times the initial cost of the system itself. Finally, Morris's ability to undertake projects with all internal resources, from initial design and engineering through fabrication and installation, all the way through field service and technical support, is a key feature of M factor. This unique ability allows us to come on board when the problem or challenge is first identified and manage the project from start to finish. No middlemen or third-party providers, eliminating the certain finger pointing that always comes if things don't go as planned. From unrivaled know-how and a drive for innovation to service after the sale and start to finish execution, M-Factor is why Morris is considered a valuable partner with all of our clients, not simply another vendor. And it's this partnership together with M-Factor that allows Morris to add real value and make a real difference in your business. Consider giving us a call if you've got a process cooling challenge we could help with.
Since you cannot get a tour of our facility because of COVID, I took a 360 view of inside our shop. This probably shows you maybe 70 to 80% of the shop. There's a lot of other areas that you probably would have seen if you came here, but this will kind of hit the highlights of it. When you saw that picture of the CEO, he was standing in front of this machine over here, and you probably can't see my pointer, but there's a kind of a machine in the background here. And that's our new laser. And what that machine allows us to do is to cut flat sheet metal into almost any pattern that we would like. And the gray thing you see here with this gentleman standing on it, that automatically feeds the flat sheet into the laser. So it can load a sheet, cut a sheet, unload a sheet, cut a different sheet really quickly. And it's super accurate. So that allows us to bend and, allows us to cut and make almost anything we want in our facility here. It then moves on over to this machine here, which is a press brake. It's also very new. It's only last 2 years. And that basically bends all the metal, and you can kind of see some examples of this bent metal right in front of it here. And everything we work on basically is stainless steel because we're doing a lot of food applications. And we do a lot of welding. What you can't see in the background behind this big machine, you see these red curtains. There's a rows and rows of those, and then behind each one of those is somebody who's welding some of the stainless steel out. We definitely have a lot of Wake Tech welders that work for us. We also have some interns from high schools that do welding for us. They have a program where I think they spend their senior year welding, and then they go to school to finish their welding certificate, all while working for us. So it's kind of an internship program. This ugly machine in the front here is just a saw that cuts. It cuts like this rod. There's a machine in the back that sprays small stainless steel BBs at the metal. That basically gives it a surface finish so that you can eliminates any scratches or fingerprints or burn from the weld. So it gives it that nice, uniform finish on there. Again, spinning around. You can't see everything, obviously, because I just stood in one spot. But we have another area back here, which you can barely see something being fabricated back there. But that's where we make our ice makers. And those are currently what they're building is a bin to hold ice, but typically they'll be building these ice makers that kind of go from the floor almost all the way to the ceiling to give you an idea of how high they are and how tall they are. Spinning out a little more. They showed the picture of this in the video. You might not have even realized what you're looking at, but this is one of the machines. This is a heat exchanger, and this allows the water to go in and get cooled. Hot water goes in and it gets cooled by refrigeration and then comes out. But this whole assembly area here is basically making those devices until it goes out the door. I merely just wanted to show you this so you can get an idea of what it looks like in this manufacturing facility. I mean, you don't get to go into these very often. They restrict people. They don't want people to get hurt. An area you can't see straight in front of us. Our engineers are kind of upstairs, and there's an electrical shop that we have that wires control panels, and we program we put our programs in these. They're like computers to control all of our systems. We also have accountants, salespeople, admin people, you name it. We have IT people. So there really is a large varying group of people that make this all come together. We are international. We're located in South America. We have a strong contingent there, probably 4 or 5 salesmen there. We have people in Asia. We sell to Russia. We just sold to Dubai not too long ago, Australia. So just a small company in Garner, North Carolina, but like a lot of companies nowadays, we are global in reach. We talked briefly about get my pointer out here. We talked briefly about the equipment that chills the chickens, and this is one of those machines. This is basically a giant auger that you put the chickens in. They slide down into the chute. The auger spins around by this drive mechanism here, and it basically pushes the birds from the entrance end to the exit end. The drive spins very slowly, and it takes about, like I said before, it takes about an hour, hour and a half for the birds to come out of the other side. What we're going to focus in on is how to size this drive right here. Now this machine is probably 10 to 12 feet wide to give you a scale of what we're looking at here. This is the cutaway section, so you can kind of see what the auger looks like inside. Like I said, wrote up there, it's like an Archimedes screw. It just spins. It is not watertight like an Archimedes screw would be to lift water up out of the ground, but this does the basic same principle. As it spins around, the front edge, the leading edge, just pushes the birds down the screw. This is an engineering drawing of the drive mechanism that I showed you a picture of. It kind of, gets rid of all the other things that are going on so we can focus on seeing the components. I'll put my laser pointer on again. It looks complicated. We got a motor here. You've got a gear reducer here. Now it's basically like a transmission. So it comes in at one speed and it slows it down. And then on the backside, you have another sprocket that's not visible. Actually, you can see it right here. And then you have a chain that wraps around this sprocket. Now this whole mechanism is designed because the motor spins at 1700 RPM, which is pretty fast. But at the end result, the auger only spins, a third of a revolution a minute. It looks like it's complicated, but when you break it down into distinct pieces, much like everything that we deal with in engineering, everything is simple machines, and it all can be broken down into smaller pieces. And then when you break it down into those smaller pieces, it's easier to understand, and then you just kind of put it all together to get your answer. And that's what we'll be doing with this thing right here. Basically, we'll focus in on the pulley here. You have 2 pulleys. These 2 pulleys seem to be about the same diameter. So you'll have a reduction that happens with the pulleys. We already talked about there's a reduction that happens inside of this gear reducer. And then there's another reduction that happens with this ratio between the sprockets. With those 3 ratios combined, it tells you how slow the shaft will spin ultimately. So a little bit of history about how you determine pitch diameter. Now this is something that's pretty common in engineering, and I don't know if it's typical in, if I ever knew this before I started doing some of this work, but you basically are comparing pitch diameter to try to get the speed of something. And pitch diameter, I stole this right off of the internet here. It basically is showing you that this is the diameter of the belt as it goes around, like this dotted blue line. Now this works for a pulley, and it also works for a sprocket. Now, and pulleys are a little different than sprockets just because of how the teeth fit into the chain, and a pulley would be something you would use on a belt. But pitch diameter is basically a universal language that everyone uses. So when you look up this part online, it'll tell you what its pitch diameter is, and it's basically the outside diameter at a specific spot. Here's the actual drive calculation that we have to do. So I just kind of set up some parameters. I said the desired speed of the shaft is 0.33 RPM. So there's a little bit more that is involved in sizing these machines, but what we're focusing on is just sizing the drive. So I'm assuming I know how fast I want this shaft to go. That's typically something that we would know because depending on the size of the bird, how cold the water is. That tells you how long you have to keep the bird in the water. If you have to keep a bird in the water longer, obviously you have to spin the shaft slower. So that's what we're going to calculate here. We know that we want to spin the shaft at 0.33 RPM. With the given information, determine what pulley diameters need to be to obtain this. The given information is 1725 RPM for the motor. That's very common in the United States. The gear reducer reduction is a 1505 to 1 reduction. That basically means for every 1,505 revolutions on the input side, there will only be 1 revolution on the output side. So that reducer is doing a lot of work in itself. The driven sprocket pitch diameter is 19.11. We talked about pitch diameter. In the driven sprocket, I've got a great image that kind of that tells you what a driven sprocket is versus a drive sprocket. Drive sprocket pitch diameter is a 6.8 inches. These are all in inches. And the drive pulley is a 3.4 pitch diameter. That's also in inches. So basically the formula is the motor RPM divided by the gear reducer ratio divided by the sprocket ratio divided by the pulley ratio gives you the output RPM at the shaft. Like I said before, we're going to break this down into individual pieces. That's the easiest way to think of this. You don't want to, you can't think of it as a whole, or you'll probably get overwhelmed with it. So you have to find these individual transitions. So the first transition was the reducer. We already know that that's a 1505 to 1. So we've got that reduction already. The next one is the sprocket reduction. Now I've basically taken the drive pulley and divided by the driven pulley. I'm sorry, the sprockets. I'm sorry, not pulleys. I've taken the drive. Just make sure I say that right. I don't want to mess it up. I've taken the driven sprocket and I divided it by the drive sprocket to get the reduction there. Now, if these numbers were reduced or reversed, that wouldn't be a reduction. That would actually speed it up, if that helps with anything. So if you actually swap these two sprockets around, you've actually sped up the shaft, not slowed it down. But since we were doing nothing but reducing, that's what we're doing here. So we're taking the known values that we had, motor RPM, sprocket reduction, gear reducer reduction, and we put those together, and we get 0.406 RPMs. So what we're still needing is the 0.33 RPM. So basically I took and did a simple, solving for X, which basically got me to the fact that I need a 1.235 reduction in my pulleys. I'm going to say that again just so everyone can appreciate it. So you have 3 different reductions happening. We know the sprocket reduction because we have both size sprockets. We know the reducer reduction because it was given. That's just, that's when you buy those, that's what it is. And really what we were just trying to find is the pulley reduction. So we found out what we reduced it already with the knowns. And so we're just trying to find what's the last ratio we need. And we found that we need a 1.235 ratio in order to get to that 0.33 shaft. So here's that image that I was telling you about. So this is basically the last piece of the puzzle that we need. And it shows the driving pulley or the drive pulley. That's on the motor. The motor is driving, so that's the drive pulley. The driven pulley is on the output. Now, these terms are very common. I've worked at least 3 places that do conveyors and anything with motors, and they all call them the drive pulley and the driven pulley. So that's definitely something that's not unique to this company. That's engineering in general. So we said we already know the 3.4 pitch diameter, and we know the ratio that we were looking for from the previous slide. So then we have the drive pulley divided by the driven pulley. That gives us the ratio. So again, we plug in the numbers we know. We know the drive pulley is 3.4 inches. So we're solving for X again here. So basically when we solve for X, we end up with a 4.2 pitch diameter. And so the driven pulley, which is again, this pulley here, is 4.2 inches in diameter.
Where it says, is that 3.4 divided by X equals 1.235? Because if you're going to do that, you're dividing 3.14 by something to get something else. So wouldn't you swap that x into the 1.235? I know that 1.235 times 3.4 is 4.2. I just don't think it's right for that problem. Your 3.4 is like your number that you're dividing something by to get the smaller number.
Yes, it doesn't make sense. Sorry about that.
It's okay, it happens.
I should have looked at the slide there. It's the opposite direct. It's the other way. 4.2
Okay.
divided by 3.4 gives you the 1.235. You can switch those around real easy and get the wrong ratio.
Yeah.
This is something that we have people do literally every time we sell a piece of equipment. They'll do these calculations. Now, you know, I tell people if they're doing hand calculations more than twice, we have a problem. Basically, what will end up happening with all of these things is that somebody will come up with a Excel spreadsheet, or perhaps there's software available to do some of these calculations. But somebody has to come up with the spreadsheet, and you have to check it, especially as everyone knows that who's done Excel. If you start messing with one cell, you didn't realize you screwed up the formula. And when it stops working, eventually you have to kind of back figure it out and go and fix it. And we've definitely had this happen. We've been using this spreadsheet to calculate these for probably 10 years. And 5 years ago, we realized that we had been calculating something slightly off for a very long time, and we had to go back in and fix it. So yeah, these calculations are happening, but a lot of times we've made our jobs easier by making Excel spreadsheets, and then we're trying to get things done quickly and accurately, and taking out human using a calculator is the fastest way to do that. But again, you have to understand what you're looking at, so you can ask yourself, does this make sense? If my pulley pitch diameter was 20.3, that 20 inches of a pulley is huge, and that's never happened before. It wouldn't even fit on the machine. So you still have to kind of not just take the answer as that's the answer. You have to kind of parse it with your knowledge and your understanding of how things work. And sometimes what we end up happening here is, we don't get all the information. We assume from previous designs that we're going to reuse maybe this sprocket here. And so maybe we just consistently try to use the same sprocket over and over again, and we just adjust some of the other pieces. These pulleys are very easy to adjust. So a lot of times that's the first thing we do. They also don't cost very much. If you talk about, well, you could have just changed out this reducer to a different reduction and got the same answer. Again, yes, you could. There's practical reasons you wouldn't. You might have some of these on hand. If you can reuse them over and over again for customers, you wouldn't change that component out. It's very expensive. And if you get more of a reduction, the cost goes up. So there's some other kind of product knowledge that people have here as to why we only change out the pulleys. But you could just as easily change out any one of these components to get to that same speed that you're after. What we have here are very typical sensors. They're throughout all of industry. These down here are valves. Now, we showed valves in some of the drawings earlier that we talked about, the water valves, that you turn valves off and let water flow through them, or turn them off and don't let water flow through them. The difference with these valves is they have an electric actuator on top of them. So basically what this does is you can send an electric signal to this, and this will turn the valve on and off. You've got a spigot on your house at home for the water, you have a handle on it, and you turn it on and off by turning it. Basically, this electronic thing is doing the same thing. It's opening and closing. What that allows you to do is that you can turn things on remotely. So I can sit at my computer and turn the valve on outside in the shop to allow the water to flow. It lets you do a lot of cool things. And that's kind of the push with you. If you've heard of automation, automating things, a lot of these items that I'm showing you here are what's really kind of driving automation in industry and other places. The ability for the computer to interact with a physical device or return, in this case, this is a pressure sensor. And so this will return the pressure inside of a boiler or some type of thing that would have kind of a buildup in it. So why you would want to know what the pressure is because some things require a certain pressure to operate. Some things require a certain pressure before they're going to explode. And so you want an alarm to go off way before that happens. And so this will send an electrical signal back to let the computer know that there's a problem. This item here is a level control. Basically, this is a long probe. It's kind of foreshortened here. It's kind of broken off, but there's a long probe that's attached to this. So think of this kind of dipping into a big tank of water. We talked about that CIP tank earlier. Perhaps you want to measure how much water is inside that tank. This probe will sit in there and it will return an electrical signal back to the machine that will tell you how high the water is. They all work in the very same way. It's all this 4 to 20 milliamps of electricity. And that's very, very common in industry. Like I said, it will return the level, the percentage it's open. So this valve might be 50% open, maybe 25% open, maybe 100% closed. Or it could just be as simple as on and off. So what I used as an example is that we were going to try to calculate the water level if we're getting a signal back to our machine that's 17.4. So we have a signal that came back to the computer that was 17.4 milliamps, but that doesn't mean anything to anybody. Basically, the signal comes back as either 4 for 0, like an off result, and 20 for an on, or like 100% result. So I get a 17.4 and I'm like, I don't know what that means. Is that good? It seems like it's mostly open, but I don't really understand what that means. So when we have to convert this to useful information for the user to use. So we have a computer screen that's going to feed back something to the operator to let them know what's happening, or to a computer to tell them what's happening. Maybe we need to open a valve to let more water in. Maybe we need to shut the valve so the water's not going in anymore because it's so full. So that's basically what this exercise is that we're going to go through real quick. How we can do this is by thinking of this as a percentage. Full is 100%, like I said, and empty is 0% in this example. They've basically got a nice graph going on here with the y-intercepts. They show the 4 milliamps here, 20 milliamps here, 100% open. Run is the percentage, the rise is the amperage. So at 20 milliamps, let me turn my pointer on. I keep forgetting you can't see it. So at 20 milliamps, we are 100% open. At 4 milliamps, we are 0% open, or it's closed, or the water. In this case, the water level is 0, and the water level is completely full at this stage. So basically, they do this. They're trying to find M in the y equals mx plus b formula. You got the rise over the run. There's your 20 milliamps minus your 4 milliamps. There's 16 milliamps. 100% signal, 0% signal equals 100% right here. In this situation, they're solving for y. What we're going to be solving for is x later on, but I just wanted to kind of show you how they got to their numbers. And then later on, they're solving for b. So we got their 1600, and they end up with b is equal to 4. So basically, what they're trying to do is they're trying to convert a percentage, and that's why they're solving for y. And they end up with a 9.5 milliamp signal, and that is they already had the 34.7% return back to the machine. We're saying that we don't have that, so we're trying to do an opposite of that. So this is the formula I have is we're getting a reading of 17.4 from the water level sensor. We need to figure out what level equates to. We're given B is equal to 4 and M is equal to 0.16 from the previous slide. And that's right there. There's the M, and the B was 4. So I basically took that information we already had from the previous slide. So here's X. I just basically plugged in the numbers. 17.4 is the Y, minus the 4 is the B, and the M is 0.16. And I end up getting 83.75%. So I've worked this a little backwards to get my percentage. So now that we know that 17.4 milliamp signal is 83.75%. Now, if I was operating a valve at this point, I would say, okay, that means that it's 83.75% open. and then we would be done. In this situation, we actually were talking about a water level sensor. So what does this mean as far as a water level sensor? So we know that the water level sensor can read between 0 feet and 6 feet. So it's basically a simple proportion to figure out what the water level actually is. So 6 feet is 100%, and we have an X is equal to 83.75%. After we do that simple proportion, we figure out that the water at 83.75% is 5.025 feet. And so we can feed that back to the screen. That's actually the information we want to send back to the HMI with, well, an HMI is what we call the screen. It's an industrial just like monitor. But we send that back to the screen so the operator sees that the water is at 5.025 feet, and then they can take appropriate action, or the computer can take appropriate action. They have set modules that they use for coding, and some of this is already in there because, like I said, a lot of things use 4 to 20 milliamps. They will already have a module that is a bunch of code that's already written for this that they'll put together and probably put a couple of those variables in, such as, how much does your water level sensor read, and things like that, and it will spit it out for them. Again, it's to try to get rid of the human error, because if you're writing code from scratch every time, you will screw something up somewhere. But they do need to understand what's going on with this. And I think I was telling Julia last time we talked, we had this set up, and I literally had one of our automation guys come in. He had put a control panel into a customer site. It was a brand new panel. They were testing it out. It was an R&D type thing. And he was getting a signal back that he didn't understand. And it was because of this calculation here that got screwed up. He was getting the wrong answer. It was basically a proportional problem. And he did a quick change of code after he figured out what was going on, and it solved it. So they do still have to understand what's happening. Even if their code is set up, it's still, they got to interpret the results that they're getting and make sense of it and go back and fix it.